Graph the following. All right, so we have this function f of x is equal to 3 minus e to the negative x. This is just a transformation of the basic graph of e to the x. Now, the basic graph of e to the x, if you don't know what that looks like, don't be intimidated by the e. It's really just a constant, right? It's basically a constant between 2 and 3, a little closer to 3, right, because it's 2.7, et cetera, et cetera. But the general idea is that if you're talking about the graph of this e to the x function, the generic e to the x function, it kind of looks like that, right? Just a normal exponential function's graph. It looks a lot like the graph for y is equal to 3 to the x. It looks very similar to y is equal to 2 to the x. Both of those graphs are very similar to each other, and this graph is close to both of those. All right, so either way, that's basically what the graph looks like. If you add 3 to it, you're going to move this intercept up 3 units. So your graph would now be shifted upwards 3 units, so something like that, right? But if you then put a negative in front of that, it's going to open down instead. So the graph might do something like this instead, right? But then if you put a negative in here for the x value, you're actually going to take this and reflect it across the y-axis. So it's going to do something like that, right? So in the end, you get, a kind of graph that should look something on the order of what I've just drawn here. Now, let's go ahead and sketch it properly by identifying the asymptote and some points and things like that. But we expect the graph at the end to look something like what I just sketched out here. All right, that's just using transformations. So let's talk about the asymptote. This little piece, the e to the negative x, not the negative sign in front, but just the e to the negative x, the smallest that's ever going to be is 0. So if you have 3 minus 0, you end up with 3. So that's basically the asymptote we're talking about here. So we expect the asymptote to occur at y is equal to 3. And this will turn out to be a maximum for this graph. And the reason why I say a maximum as opposed to a minimum is because the negative in front of the e means that this thing can get very, very tiny. So for example, if you were able to get e to the negative x to be something like 1,000,000, by putting the negative in front, it becomes negative 1,000,000, right? So it's going to basically go down from there, the graph, because of the fact that that negative sign is going to make any value for this term basically negative, right? Okay, so again, we can never achieve the 3 here, but we can approach that 3 asymptotically. All right, so we have the asymptote there. Now let's go ahead and try to plot some points, right, to finish up the graph. So some good points to use, as always, are things like -2, -1, 0, 1, and 2. Okay, so let's go ahead and put in -2 and see what we get. So we'll have 3 minus e to the negative 2 power. That's the same as saying 3 minus e to the second power, which if I evaluate with my calculator, that will become approximately -4.4. If I do the same thing, but this time plugging in -1, I'll basically have 3 minus e to the 1, right? Because -1 would make this e to the 1. And if I evaluate that, I will end up getting 0.28, so let's call it 0.3. And then if I use 0, it'll be 3 minus e to the -0, which is the same as 3 minus e to the 0 power. And that, of course, is the same as 3 minus 1, or 2. Now let's plug in the 1 and the 2. So we'll put in 1 first. That'll be the same as 3 minus e to the 1 over e to the 1 power. And that will work out to be 2.6 approximately. Now if I do the same thing and this time putting in 2, it'll become 3 minus e to the -2, which will be the same as 3 minus 1 over e squared. And that will give me approximately 2.9. Okay, let's go ahead and plot these points then and see what that gives us. So -2 will give me -4.4. So -2, we go down to about 4.5 almost, right? So around there. And then -1 will go down to 0.3, so it's not very far, maybe about there. And if we have 0, we are at 2, so we're here. And then if we're at 1, we're at 2.6, so maybe about here. And then if we're at 2, we're at 2.9, so getting very close to the asymptote about there. All right, now if we connect those points, we're going to get something like this, right? All right, so there it is, basically the graph that we had sketched out by hand a little bit earlier. If you're talking about the domain and range for the function, you can tell that the domain would be all real numbers again. So the domain is basically from -infinity to +infinity, while the range actually goes from what? -infinity on the y-axis up to 3, but not including 3. Remember, we don't actually achieve 3 in this graph. right, let's take a look at the graph for b then. For the graph for b, it's a similar idea. It's basically a transformation of the e to the x graph. Let's just go ahead and get right to the asymptote part of it, and then we'll talk about plotting points. So when you look at this graph, you can see that this piece of it, no matter what you put in for x, won't be any smaller than 0, right? It's going to grow from there, but it won't get any smaller than 0. And of course, if that becomes 0, then this becomes 0, so you end up with 1 minus 0, or 1. Now, that again is going to be a maximum because this negative here is going to make anything when this becomes positive become ultimately negative. So the point is the maximum here is 1, so we expect an asymptote right about here for the graph. Again, what I said about it becoming 0 or smaller than 0, it won't actually ever be 0 as we've talked about before, right? It just asymptotically approaches 0 because, if you put in negative values for x, that e to the 3x will start to get small, and then if you put really, really small negative values, it'll start to get very, very small, and it'll get something close to 0. So either way, the point is the asymptote is 1 because we will approach that but never achieve it, right? And again, in this case, it happens to be a maximum for the function. Now, looking at the rest of the graph will really be a matter of just plotting points and then thinking about what's going on with this 3x that's happening here and what's going on with this 2 here. All right, so now that we have the asymptote, let's go ahead and plot the points that will help us draw the graph. There are some transformations that are going on here. Obviously the +1 has moved the graph up a little bit. This -2 the minus part has reflected it downwards. The 2, of course, is going to have sort of a stretching effect on the graph. Same with the 3, they're kind of altering the values that go in for x. But either way, regardless of that, let's go ahead and pick some values that will work well here. If you want to use the traditional -2, -1, 0, 1, and 2 points, you might want to modify them based on the fact that when you plug them into 3x, right, they're going to be a little bit different, right? In other words, if you want to get the equivalent of a -2 plugged in for x, then you really got to think, well, when is 3x equal to -2? Does that make sense? If you did that, basically you'd say x is equal to -2/3, right? Because you're solving by dividing by 3. And likewise, if I said, well, when is 3x going to be equal to -1? Well, it'd be when dividing by 3, x is equal to 1/3, right? And, x, of course, 3x will be equal to 0 only when x is equal to 0. So basically, if you want to change these to the equivalent points that are going to work for this function, you might try -2/3 instead of -2. You might try -1/3 instead of -1, then 0, you can keep the same. For 1, we'll try 1/3, and for 2, we'll actually try 2/3. So let's plot those points instead of the traditional ones that we plotted in the past. And if we do that, let's see what happens. If I plug in 1 minus 2e to the 3 times -2/3, well, the 3's cancel out, and I do get e to the -2, so it'd be 1 minus 2e to the -2. Well, for that, you get approximately 0.7, rounding it off to 1 decimal place. Let's do the same thing for the 1/3 then. See what happens when you plug in 1/3. Just to save time, I'm going to do this quickly in my calculator because otherwise it takes a while. So that'll give you approximately 0.3. If you do the same result with 0, we can evaluate by hand pretty easily. So let's do that one by hand. If you have 1 minus 2e to the 3 times 0, it's going to be the same as saying 1 minus 2 to e to the 0, which is the same as 1 minus 2 times 1, or 1 minus 2, which is -1. And then if you put in the 1/3, you'll get -4.4 to 1 decimal place. And then if you put in the 2/3, you'll end up with a number like -13.8. So very much off our chart. Okay, so let's go ahead and plot these points and see what we come up with. So if I put in -2/3, I get 0.7. So -2/3 is about here, right? And if I put in -1/3, I get 0.3, so maybe that's there. If I put in 0, I get -1, that's here. If I put in 1/3, I get -4.4, so then we're all the way down to maybe here. And then if I put in 2/3, I get all the way down to -13, so you can see why it was important to adjust the points because we're already dropping way off our drawings. Let's kind of put it there, just kind of put the point on the screen somewhere. And then from there, it hugs this asymptotically, so it's going to look kind of like this. It's got a sharp drop, and this is from those stretches that we're getting. So it's kind of like that, the graph. That's our best sketch by hand. And if you talk about the domain and range for this function, again, the domain is all real numbers. No restrictions on what we can put in because there are no fractions, no radicals, nothing like that to worry about. For the range, though, we're basically going from -infinity on the y-axis, right? Because we go all the way down forever and ever. and we rise up to 1, again, not including 1. So that's the domain and range. You have your asymptote drawn, and that's the end of the graph.